All right, hello everybody. So I posted the homework one solution, but I think I made a mistake on when I was writing it. I'm gonna show you where I'm gonna fix it, but just since you're gonna be checking your homework. So here for this question 4, when I multiplied here, I added here instead. So this is gonna be a multiplication, but you've been graded based on the correct version. So I'll fix this, but just so you know. All right, I also added homework, class participation 4, 5, and 8 solution to Carmen. So you should have everything up to 8. I will add 9, which I made a mistake in the quiz. I will write what would be the correct answer for the question you saw, because a lot of you said none of the above, which was correct. But the point was to see what you got. So I will post that for 2 cases, the actual question and the question that I was discussing in the class at the end. All right, to just clear the confusion. I didn't didn't have time to record a separate video for this lecture that didn't have, I didn't have my HDMI cable, but I'm just gonna go over this really quickly. So it will be part of this lecture. Basically, what are the steps to solve this problem? And then we will go about and finish the examples, all right? So whenever you get a system and you are asked to obtain the state space representation of it, basically we are asking about that first order differential equation for state equation, and then the output equation, which is a design decision. So if you didn't have any information on what the output looks like, you can just say, assuming output is this, create it. But if you had output, you just form matrix C and D based on that. So step 1 always is to obtain differential equation of a motion, as you can see here. Now, sometimes you have the differential equation. Instead of having the system, you just have the differential equation. So step 1 is done for you. Step 2 will be change of variable. Now, we will use change of variable because if you had second order, third order, fourth order system, this is a better way, easier way to do it. Is the same as if you said, I know what my state vector is, I'm just going to write the state vector, and that's the same as getting a different variable, change of variable. These are the same things, but I think having change of variable, you can solve all the problems, even if you don't know exactly what your states are, state variables are. So step 2 is use of change of variable. Step 3 is getting the derivative of that change of variable. So the idea was, if you remember, instead of having y dot, I wanted to get rid of that. So Z1 and Z2, which are equal to y and y dot. Now I'm going to write my equation again. And when you write the equation, you will have a first order system. Now from that first order system, like Z dot 1, Z dot 2 here for that example, next step is put it in my matrix form. It's easier to see because if you remember, this was our form, right? We had x dot here would be AX. So the goal is to make it look like first order and then write that ABCD matrix. All right, it's always like that. So whenever you are dealing with the state space representation, the goal is to make it look like first order, then derive ABCD, and then just use those as we go forward, right? So that was the example we solved. I solved another example that we had third order. So we needed 3 variable, right? And then we solved, converted to first order, and then drive the equation. So hopefully you reviewed or at least remember what happened last time. There is another example for this one. I'm going to actually solve it. I'm going to go back to my clean version. Nope, not this one. Sorry, state space. This example. For this example, I'm just gonna drive up to the variables. From there is easy, you can do it yourself. Now, there is a point in this example which I want to show you. Now, let's say this is our system. Mass spring damper is multi-mass. We have M1 and M2, right? So if you wanted to get, what would be the first step to solve this problem? Free body diagram and get the differential equation, right? So let's do that. free body diagram, I'm gonna start. I usually start from where the force is applied because I know that that would define with the motion, which way we would move. And then if it's connected to another mass, I know what would be the input of the second system. So U goes here, U of T. I know that I have dash plot here, Bx. Well, here my displacement is called Z. So this will be Bz dot. And then here we have Kz. So these two want to oppose the motion, which is U, right? We have one other force here. What's that? Inertia. M2, since this is Z double dot, also wants to oppose the motion. Now, I think, Connor, you asked a question like in the class participation. Why do we use, for example, ZF equal to 0 as opposed to ZF MA, right? Does anybody know the answer? What's the difference between these two? There's none. They are the same. So this, if you write it like this, it means that the summation of all the forces applied on our system is equal to 0. So inertia is one of the forces applied, or summation of all the external forces applied to our system is equal to mass times acceleration. So either count mass times acceleration as inertia as part of forces applied on the system, is internal, right? Or say that, okay, everything else added is equal to how much acceleration my system will get. They're both the same. So I usually use this myself because that way, when I draw free body diagram, I show all the forces and then I just put them, like add them together. If you go with this route here, then you don't need to show that. That is basically this, MZ double dot, right? So same thing, but two different, like a slight different definition. So I prefer to show which side, how inertia is being applied, and then write summation of F equal to 0. If it was rotational, summation M or tau is equal to 0, because I know that's how the Newton's law holds. All right. So both of them are the same. If you saw me using interchangeably, because you can, but you have to be careful to count inertia one time. Don't count it twice. All right, so this is the free body diagram for the first mass. Now for the second mass, M1, which will have the displacement of Y. So now, since mass 1 is impacted by mass 2, I know whatever forces from mass 1 in the opposite direction, right? So I know that there should be. Now here, I quickly realize, I didn't consider the part that these two are interacting. So this will be Z dot minus Y dot, Z minus Y. Then this is just the same force, opposite direction. Z dot minus Y dot. This is K, Z minus Y. So if you did that, you forgot to count for the other mass. The easier way, like the easy way is like just what I did. Oh, I forgot to count for the other masses effect. You just added. So now this is the free body diagram. All you have to do is write the equation of motions. Now, how many equations do you expect to get from here? How many sets? Two sets of second order differential equation, right? So I'm gonna just write down the final equation. You just have to put them equal to 0. So your equation of motion will be M1 Y double dot minus negative Z dot minus Y dot. Hopefully I put all of this correctly. Z minus Y equal to 0. And the other set is M2 Z double dot plus B Z dot minus Y dot plus K Z minus Y equal to UT. So this is for this one and this for that one. All right, so I get this, the two equation of motion. I expect it because I have two masses. Now, do you remember? So next step is to get the change of variable, right? That was step 2. So how many change of variable do I need here? Do you remember how would we start with educated guess?
Do 2, the second order.
Okay. So let's say, so is it second order 2? How many second order do we have here?
2.
2. So it will be 4. 2 for one, 2 for the other one, right? Because if you look, the way that the displacement are here, one is z and one is y, so like 2 different displacement, right? Each have one set of equation. So total will be 4 variables. So every time, if you have y double dot, you need 2 variables. So z double dot, another 2 variable. So I'm gonna say option 1, because there's a kick here. I'm gonna say option 1, the way that we always know and is always safe. Let's say I'm gonna call all my change of variables x. This means that my state variable is gonna be x1, x2, x3, x4, right? 4 things. Then I'm gonna call my x1 is y, x2 is y dot, x3 is z, x4 is z dot. Do we understand why I got the change of variable like that? If not, ask question, I'll explain it right now. Yes. So if you look at here, what is y? Displacement, right? So if you think about the state vector, it means that I want to measure the displacement, how much it goes from one place, the position, right? What is y dot? Velocity, right? So for mass number 1, I'm looking at position and velocity. For mass number 2, z and z dot, I'm looking at mass and velocity of that one, right? So in total, I have 4 variables that I want to measure. So this is called, so I call those variables in a system that I'm trying to measure as my state variable. So your state variable is actually y dot, z dot. If you can realize this, you don't have to do change of variable. You can just go directly here. But to make it simple, we say, you know what, I'm just gonna call it x1, x2, x3, x4. So I don't have any dot or anything. I'm just changing their name for now. Okay, that is all change of variable mean, just to get that dot out of our face, right? But they have a physical meaning. We are doing something meaningful. So every time you have mass spring system, per mass, you want to look at position and velocity, basically, right? So I'm gonna keep this for now here, here, because I'm gonna do that later. All right, so this was a step 2. Step 3, what was it? What would I do here from here? Derivative of those, right? x2, x dot 3, x dot 4, and then this becomes y dot, which is our x2. This becomes y double dot, which we get it from our EOM, right? From EOM. Then x dot 3 is z dot, which is our x4. And then x dot 4 is z double dot, also from equation of motion. Correct? And then we write the matrix form. That's the last step. Get A, B, C, D. So there is another option when we are defining our state variable vector. The minimum number that you absolutely need is the number of components that restore energy. So how many components together we have there that will restore energy? As inertia is kind of restoring energy for us because it's m a double dot. So all of your masses, let's say plus all the other items that are restoring energy. So that's probably easier. So we have 3 dashpot waste energy because it's like friction, right? So if you have 2 masses and 1 spring, can be restored, like can save energy, and then if you let it go, it just changes the type of energy, right? Yes.
What if you get from
So here, where do I get y double dot from? So here, if you look from this guy, I can put everything on this side. Y double dot is B M1 Z dot minus Y dot, and then plus K over M1 Z minus Y. That's where you get it from. So I'm going to keep it there, but the other one from equation of motion. That's always how it works. You always have to find it from equation of motion. Now, option 2, because we just counted, we have 2 masses and 1 restoring. So at minimum, I need to rechange a variable. Can you suggest a change of variable that would cover everything here for me? So I'm going to say new x1, new x2, new x3. I'm going to argue I only need 3 at minimum. So 4 is fine. If you go with 4, totally fine. Okay, but there is a minimum, which is 3. Now look at this. If I say this is y minus z, this is y dot, this is z dot, then x dot 1 is y dot minus z dot, x dot 2 is y double dot, x dot 3 is z double dot, right? So this from equation of motion, this from equation of motion, this guy is y dot minus x dot. So it's x2 minus x3. So I could write all of them. They're all changed to new variables, right? And from EOM, we just saw y double dot is going to be based on z dot, y dot, z, and y, which we have it in our equation. So this is not absolutely needed, but if you could see, if you get this kind of change of variable, it just makes your computation less. How? What would this do to our state space representation matrices? Getting 3 change of variable instead of 4.
That's where we need 4 state vectors.
If there is 4 state vector, you will see the impact on what? What will change? What will change? So do you remember x dot is a times x? So instead of having a 4 by 4, you're going to have a 3 by 3. That's where your calculation is smaller. Now think about this was a spacecraft. You had like 10 mass system. So if you could relate them with, if they were dependent, so these are dependent state, right? If you could find that, it would just make your calculation easier. But if you didn't see it, it's totally fine. You could say, I have 2 equations of second order, I'm going to get 4, you'll be fine. You just have a bigger matrix. For our applications, the worst case scenario is like 4 or let's say 6 by 6 or 4 by 4. You're not going to have bigger than that. All right. But if it was real life scenario, every minute, every second matters, is money, then you want to find those things. So this is kind of an information trivia for you. Yes.
Are we losing any information by combining the y?
No, you're just saying that y minus is relative. They're moving together, right?
Yeah.
So you basically, at the end of the day, if you want to track, you're going to say that the position, these 2 are moving together. That's all. The information you lose is how much M1 is moving separately than M2. But if your application didn't care, if there was a flag up here, you want to know how much this flag is moving. It is moving y minus z anyways, right? So you didn't lose any information. But if you had 2 different flags, let's say, and you need to know exactly how much each of them are moving, then you had to go with option 1 and get them separately. It becomes the definition of what do you want to be your state vector, right? What are you controlling? If I'm controlling the relative distance that these 2 travel together, then I will probably go y minus z, because I've been asked to control the relative distance. But if I was asked to control them separately, I'll go with option 1, because my state vector are position of the first box, position of the second box, velocity of the first box, velocity of the second box in option 1. Option 2 just says velocity of box 1, velocity of box 2, and the relative displacement of these 2 together. All right, so simpler system. But when you are looking at these kind of problems, you have to actually look at the system, how it moves, right? So you have to have an understanding of the state vector. All right. This was part of one of the lecture. I actually never got around doing it. But now it would be easier because you already know what kind of motion is this? Is it translational or rotational? Rotational motion, right? So for rotational motion, we have to find the torques, right? Equal to either you can write J alpha or I alpha, or again, you can say sigma tau equal to 0. So you will see that J alpha inside of it. So summation of all the torques applied to the system is equal to the rotational velocity times inertia, so rotation acceleration, or all the torque applied in internal and external is equal to 0, right? Now, how do we get, what point do we get the torques? Some point for a pendulum that's moving. So let's say this was a rest point, and then you moved it. So which is the point that we will calculate the torques? So if I move this, would the length of this rod change? So as you move, this length stays the same, right? So it's kind of a pivot point. So the pivot point is the point that you get all the torques about. All right. So this would be a pivot point. I'm going to get all the torques here. So let's say this was mass M, right? This is theta. This is mg, and this is L. Let's say there is no other external forces. It's just we move it there and we want to see what's the summation of the torques. We can say that mg, well, this has to be divided by its component. So let's say going this way and this way. This element mg cosine of theta, this is mg sine of theta, is in front of theta. Cosine is going through the pivot point, so there is no torque from it. The only torque is from the mg sine of theta. And this is the distance that the lever, right? So this is the lever, the distance of the lever. So it will be mg sine of theta times L. That's the only force, the only torque we have equal to this part, which is the moment of inertia, right? So I times theta double dot. What is I for a rod with a ball or with a mass at the end of it? You have to remember this. So the inertia for different, moment of inertia for different object, you have to remember or look up. So it would be ml squared. So this is ml squared theta double dot. So our equation is ml theta double dot minus mg sine theta, mgl sine theta. Equal to 0. Now, can I use this to convert this to state space representation or write a transfer function for it? Can I use this equation? This is the differential equation of the system, right? It's just instead of y or x is theta, theta and theta double dot. Can I use it as it is? Michael? No, you don't know? Kevin? No, this is just second order differential equation. We have one mass, one second order differential equation. Remember definitions? That's why they are important for transfer function. It has to be an LTI system. Is this an LTI system? It's not. Why? Why makes it not to be an LTI system? Sine of theta, right? Because theta is a variable. Sine of theta is not linear. So we have a problem here. So this is not linear, but if we look at the response, we will see that for a good amount of time, this actually behaves like a line linearly, not like a line, linearly. So we can say that for small thetas, we can write this equation. We can say sine of theta is equal to theta. Now for this, you can go back to lecture annotated version. We use Taylor series to show this, but always for small values of theta, we can linearize sine of theta and say is equal to theta. Now equation becomes ml squared theta double dot minus mgl theta. Now, is this LTI? Yes, because, well, the coefficient of this is a fixed number, constant number. This coefficient is a constant number. Theta and theta dot, double dot are as expected, just the derivative of our vector, right? The state vector. Now this is LTI. Now we can use this equation. So every time you see pendulum in any of the systems, you have to use the linearized version. So this is linearized. This is non-linear. So this is not LTI because it's not linear. Doesn't have to do anything with the time part of it, right? So you will see if you are using the book, I hope you do. There are a lot of examples in the book. I don't have time to do all the examples. You will see a lot of inverted pendulum, actual pendulum, pendulum connected to each other. For all of those, you have to linearize, and that's how you do it. All right. One of the example of the book, your textbook, is this one. I'm not going to solve it. I want you to like at least review this and try to see if you can solve it. And I'll record a video and post the solution. So I won't use the class time, but it will be a recorded video. All right. So you have how many pendulum you have? 2. These 2 are connected with a spring. So you have 2 rotational motion and a linear motion. So this is complex enough. It has everything in it, right? So you can't just solve. You have to pay attention that these are 2 different things connected. All right. So take a look at this. I will post. I try to post it by the weekend. So if you're in a study, you have time to do that. All right. You should be able to solve this by the information you have, but it's complex. Compared to everything else we did so far, this is the most difficult example you can get. All right. So we'll post the solution. But this is for you to spend some time. This is a lamp. I mean, not lamp, but light. Supposed to be light. Here needs a battery. Plus, minus. There you go. Good on this one. Yes. Questions? I already posted the annotated version of this. I'm going to post it again in today's page, so you have all the information available to you. Now I'm going to go back to today's lecture, which is very short, to finish off state of space representation. I'll give you a minute or 2 to breathe. Breathing is important. And I am not muted. That's good news. Not next week, the week after, we have our first exam, right? Exam 1. It's in person, it's going to be here. if you registered SLVS, it's going to do that. I'll send the questions over. In my exams, you can bring cheat sheet. So why am I giving you this information? If you're studying over the weekend, start putting your cheat sheet together. One side of a US letter or A4 size paper, you have to write it down. You cannot type it. You only have to write, you can only bring the equations. You cannot bring any solved problem or example. You cannot explain the example for yourself in the cheat sheet. But you can write a procedure how to do it in English. So you can say that for state space, step 1 do this, step 2 do this, step 3, but I don't want to see anything solved. This way, if you haven't studied, that will be your study for the exam. So if you want to start preparing your cheat sheet, go ahead. You will submit your cheat sheet to your exam. We will grade your exam by looking at your cheat sheet. So if there was any solved example, you'll get a 0. If you are using an equation that's in your cheat sheet and that's everything you put on the question, you don't get any point because you brought it. So because I usually give point to any effort you make to train up your thoughts. Sometimes my students, they just write down how they would solve it if they remember the equation and they get a good bit of the points. Yes. No, you bring everything you think you need for yourself. But then you can't write the transfer function of an op-amp. You're supposed to be able to drive it. Exam is 55 minutes. I'm gonna design the question for 30 minutes worth of your time, 30 to 35. So when you're studying, think how much this question takes time to solve. If one question takes you 30 minutes, how is not gonna be in the exam? Study smart, all right? Yes.
Are you gonna post like any practice?
Yes.
For previous exams?
So week 6, Friday, I already created a quiz for type of conceptual question I'll give you. So that will be a quiz for you to do over the weekend. Then I'll also post problems. So on Friday of week 6, you will do the problems here together. I recorded, posted. I'll also give you the layout of the exam so you see what kind, like how many questions you will see, what are the instructions, you will see everything. On the exam, you just have different questions. So who had class with me before? I'm not a hard exam taker, am I? Like robotic? No. Am I? There's always tricky questions though, because it's always related to the concept. So if you know the concept, I'm happy. All right, so my exam grades are usually high, but if you understand, for example, if you understood the state vector, any question I give, you should be able to do it. But I will give you the question inside the exam time. So be smart when you're studying. Don't do problems that take 1 hour. It's not gonna appear in your exam. All right, let's do this one. I'll give you more information on week 6. Don't worry about it. Just wanted to tell you if you're studying, you can start preparing your cheat sheet. So we learned 2 methods of representing a system. Transfer function, which is in the S domain, state space representation, which is in time domain. We should be able to convert from one to other without actually driving it from the beginning. There is a way to do that. So let's say this is the form of our transfer, a state space transfer function. We are in time domain, right? Now to go to S domain, what do you think I should do? What should I do to this time domain equation? I can beat it, but it would not change to S domain. I know you know, but I want someone to say it. Sam?
This is Fourier transform.
The other one.
Inverse.
Fourier takes us to frequency domain, right? What was it? Laplace, the other one, right? That's the other one. So we have 3 things. So it was like 50-50, you got the other 50. So get Laplace. We don't get transfer because we want to go to Laplace, not the other way around. So get the Laplace transform basically means that we want to get this, which is the output over input. How to do that? Very, very simple. This is x of s, x of s, a x of s plus b u of s, because a, b, c, d are numerical values. Then this is y of s is c x of s plus d u of s. Well, we now have two equations in S domain, but we need to find this expression to be transfer function, right? So we have to get it from these two. If I reorganize this and write x of s, basically bring ax of s to the left side and factor that out, is s I minus a, right, equal to bu. I want to pay attention to here to see what happened right here. What happened there? So the equation looked like s x of s minus a x of s. Then I said, I'm gonna factor out x of s. Then instead of writing s minus a, I said s times I is the identity matrix. Why did I do that? What's wrong with s minus a? Mathematically. S is just like one dimension value, right? It's 1 by 1. It's not a scalar, it's a system type. But S on its own is 1 by 1, it's just one number. How about A? What's the dimension of A? Depends, n by n, right? Whatever. So anything more than 1 by 1. So to do that, we can say S times I minus A. Now, if our A is 2 by 2, we actually have 1, 0, 0, 1 minus that A that is 2 by 2. So it's like S 0, 0, S minus. Now we can mathematically perform this. So remember, this I is important and where it came from. So that this is where your previous knowledge is coming in handy, right? So taking math was not useless. All right. Now I want to find x of s from this guy. So x of s is pre-multiply the inverse times bu of s. If you don't remember why it's pre-multiply, you can go to Wikipedia and find out. Instead of going back to your previous lecture's textbook, it's quick to do that. It's always going to be, if you bring it from here, it's going to be pre-multiplied. All right, so I have an expression for x of s. Now, here, if I plug it in this equation for y of x, I have c, then si minus a inverse b u of s plus d us. And there you go. US, I can factor that out. C, S, I, negative A, inverse B plus D. All I have to do to get my transfer function is to bring U in the denominator, right? So YS over US is C, S multiplied by the identity, A negative 1, B plus D. Good news, this always is fixed. That's the relation between transfer function and state space. So if you have A, B, C, and D matrix, you just need to perform this operation to get your transfer function. So you don't have to actually solve the whole thing from beginning. So it might be a good idea if you're more comfortable with transfer function, solve transfer function, convert. Yes.
What is the dimensionality of the transfer function? Would it be scalar or could it be?
So transfer function is going to be in what domain? S domain. So it's going to be a system type. So it would be a function of S in the numerator, a sentence polynomial over a sentence in denominator. When we are in S domain, we don't have, what was your question?
My question is, why of S over U of S? What is the dimensionality?
Okay, for that, we don't have a dimension. So we have polynomial, and then we have the order of the polynomial. So if in the numerator you had S, and in the denominator S squared plus something, so numerator order is 1, denominator is S squared 2. That would not matter much for you, only for the finding pole and zeros. That would tell you what's the order of the system.
So would B necessarily be?
Oh, here, oh, that's what you're asking here?
Yeah.
Okay, yes, all right. Depending on the system, so if A is 2 by 2, so this is 2 by 2, so this is 2 by 2, this is something by 2, and this is whatever this one is by 1, which is 2 by 1. Yeah, that's how it would be. So I thought you mean dimensionality on the left side. Left side doesn't have any dimension. Right side, so the thing is you always have to make sure mathematically this is possible, this operation. And the trick is to find what is the dimension of A. Once you have that, everything else should pan out. And you should be able to do that operation. So you will not have 3 inputs for a 2-dimensional, for like a 2 by 2 A matrix. So it has to be 2 by 1. All right, for B. So these dimensions always should match and would match as long as you have A correctly. If you form the A correctly, everything else will match. All right. So we'll do a quick example to see how it works. I'm gonna keep that on top so you can see. You have to use this information. So if you're bringing a cheat sheet, that has to be on your cheat sheet. How to go from a state space to transfer function. Now, find the transfer function for the state space representation matrix below, A, B, C, D, right? So this system is 2 by 2. Here is 2 by 1. This is 1 by 2. This really doesn't matter, D, 0, because it's 0. Now, we need to form YS over US. We can use that equation. I'm just going to write the matrices. C is 1 and 0. So first is C, then multiply by S times I. I'm not going to put anything in I don't know what it is right now. Minus A. A is 0, 1, 2, negative 3. So this is 2 by 2. For us to be able to do this operation, this has to be 2 by 2 as well. So now I know what's the dimension of I. So that is going to be this matrix that I need to find the inverse of it times B, 1 and 0. So that's for this part plus D, which is 0. I'm just going to write under what each of these are. This is B, this is I, this is A, and this is B. All I did is I just wrote that equation. Now, performing that, 1 and 0, I can multiply. So this is S, 0, 0, S, 0, 1, 2, negative 3. I have to find, well, I'm going to use this so you can see the inverse of this, and then multiply by 0 and 1. So I'm going to do this guy. So it's S, negative 1, negative 2, S plus 3, inverse 1, 0. Now, do we remember how to find the inverse of a 2 by 2 matrix? And almost.
More complex or bigger one.
So the flip-flop part is the adjunct, which let's say for A, B, C, D inverse is going to be D, A, I'm not wrong, negative B, negative C. So that's the flip-flop. And there's so this is called adjunct of X over the determinant. So here, adjunct over determinant of X. So you can keep this. I'm not going to give you more than 2 by 2. So that's good. And the determinant is AD minus BC, right? So to find the inverse, you have to use that. Now, if it's your exam, you're using your calculator, you still have to write this equation for me. You have to write it here, but you can plug in the values in your calculator to show me you know how to do it, but you just want to be quick using your calculator. So if you do that, you get 1 and 0. Where did I write it? S plus 3, S 1, 2, right? Then divide by S times S plus 3, negative 2, times negative 1 by 1 and 0. Now I can, so that I have 3 matrices and 1 sentence, 1 polynomial that's based on S. I can take that out, right? So I cannot, I don't get confused. 3S plus 2, negative, minus 2, right? Minus 2, not plus. Minus 2, and you have 3 matrices, 1 and 0, S plus 3, 1, 2S, and 1 and 0. If you perform this, you're gonna get, I'm gonna write it up here, S plus 3 over S squared plus 3S minus 2. So this is mathematically doable. 1 by 2 times 2 by 2 times 2 by 1. Answer to your question. That's how you find the dimensionality of that. And this is our transfer function. Numerator S plus 3, denominator S squared plus 3S minus 2. It's squared, is not cubed. Before you kill me. Yes, I saw that in your eyes. Okay, so that's your transfer function. You're gonna have 2 poles, right? We just know, we just need to find what the 2 poles are. You're gonna have 1, 0, the 0 doesn't really matter as much. We'll see later. So that's how you go. Convert from transfer function to state space by hand. Well, from state space to transfer function by hand. All right. There is one other thing that I want to add. So now, so what? Like with transfer function, we can take a look at poles. And I told you, I'm always telling you, poles are really important to find if the system is stable or not stable. Okay. What if I had this state space representation? How would I know from that if the system is stable or not? Or what are the poles? What are the poles of system if I only had the state space representation and I didn't want to find the transfer function because I don't want to do all of this? You should be able to find that, right? Is the question clear?
Just lines up like that.
So it has to do with this guy. Can you guess why? What? Yes.
Needs to be vertical.
Yes, but that is a very mathematical way of saying it, which is correct. Now, let's take a look at SI minus A. What are each of those? And which one of those 3 tells us something about our system? A. The only expression in that whole thing here that tells us something about the system is wherever there's A, right? So A is the system, poles are the specification of our system. That's why we will use SI minus A to find our poles. Now here we get the determinant and put it equal to 0. This is how we calculate eigenvalues. Bringing bad memories for everyone. Yes, I remember myself. So eigenvalues of a system in time domain represent the poles of a system in S domain. Everything has to be connected, right? They have to be correlated. So if you had a state space representation, you get the eigenvalue or you calculate determinant of SI minus A equal to 0 to find what S's satisfy that relationship, and those are your poles. And if you don't believe me, you can solve for this. So in MATLAB is like eiga, and it gives you 2s. You can find this s squared plus 3s minus 2 equal to 0. You find 2s. These two will be equal. If you do this, this s is going to be negative 3.561 and then 0.561. Same here. And if you used this, plug in A in here, you also get the same S. Negative 3.561, 0.561. So the poles of a system, if you are in S domain or if you have the transfer function, you grab the denominator equal to 0, you find the pole. If you have the state space representation, you find the eigenvalue, which is determinant of SI minus A equal to 0. They will be the same. So you don't actually have to go from one system to another to find the poles. If the eigenvalues are negative, your system is stable. If the poles are negative, your system is stable. If you don't have eigenvalues, your system is not invertible, then there are others, like it's not controllable. This is more advanced control stuff, but it comes all from the system of what is eigenvalue. So this will be basically the part of the lecture that is important. We'll go to your exam. This one is a extra note. We are running out of time. This is bonus because it is in your book. And I thought if you read the book, you would get confused. I'll touch base on this on Wednesday. Today's Wednesday. On Friday before we start MATLAB. Friday's MATLAB, be here or be squared and bring a device. All right, or sit next to someone that has a device. What? Oh, okay. Class participation is, oh, sorry, thank you. You have time until midnight tonight. And it's just what we talked about today. No, no Pascal. This is just the practice of the lecture. I want you to do it. Don't forget. Thank you, I forgot that.